Welcome to part 2 of invertible elements. Today we will be looking at the Euler function and its theorem, and also the Fermat's theorem, and try as much as possible to solve questions under them. Okay, so let's start. Let's start with the Euler function. The number of invertible elements of a ring Zn is denoted by rho of n, and it is called Euler's function. Thus, if you have rho of n, then this is E Zn, the GCD of E and n is equal to 1. And we talked about this in the previous video. Okay, so the theorem. If P is prime and K is a positive integer, then rho of pk is equal to pk minus pk minus 1. Also, if m and n are co-prime, then rho of m n is equal to rho of m dot multiplying rho of n. And the last one is, if p is prime, then rho of p is equal to p minus 1. Okay, so now let's solve some examples for you to understand what I just wrote. So the first example is, if we have rho of 49 over here, in this case we can rewrite this as rho of 7 squared, and that is what we have over here. So if p is prime, so in this case our p is 7, which is prime, and k is a positive integer, so over here 2 is a positive integer, so we can rewrite this, we can rewrite this as 7 squared minus 7 exponent 1. Now from the theorem it said that if we have pk, then this is equal to pk minus pk minus 1. So in this case we have 7 squared minus 7 exponent 1, and this is equal to 49 minus 7, which is equal to 42. So rho of 49 is the same as 42. Okay, what of rho of 36? Is this equal to this? Is it equal to? No, because this 6 over here is not prime. If it was to be prime, we would have done this. But 6 in this case is not prime. So this is not equal to this. Now, if this is not equal to this, now how do we solve this? In solving this, rho of 36 is equal to. Now if you have this, you have to break this down into its prime numbers. So prime multiplication to get 36. So 36 is the same as writing 2 squared times 3 squared. And now 2 squared times 3 squared is the same as 4 times 9. And if you have 4 times 9, so remember the m and n. If m and n are co-prime, so over here, in the second one, if m and n are co-prime, then we can rewrite this as rho of m times rho of n. So this is rho of 4 times rho of 9. What do we mean by co-prime? Co-prime in the sense that GCD of 4 and 9 is equal to 1. So now let's find rho of 4. Rho of 4 can be rewritten as rho of 2 squared. Now is 2 prime? Yes. So we can write this 2 squared minus 2, 1. And this is equal to 4 minus 2, which is equal to 2. Rho of 9 is equal to rho of 3 squared. Is 3 prime? Yes. So 3 squared minus 3, which is 9 minus 3, which is equal to 6. So now rho of 36 is equal to 2 times 6, which is equal to 12. I hope this is clear. Okay, let's solve another one. Let's find rho of 35. Again, we can resolve this equation into this. 5 times 7 is 35, and the GCD of 5 and 7 is 1. So we can resolve this as rho of 5 times rho of 7. And remember the last theorem. The last theorem said if P is prime, then rho of P is equal to P minus 1. Now looking at this, 5 and 7, they are both primes, right? So we can rewrite rho of 5 to be equal to 5 minus 1, which is equal to 4. And rho of 7 to be equal to 7 minus 1, which is equal to 6. So in other words, rho of 35 is equal to 4 times 6, which is equal to 24. Okay. Now let's move on. Let's look at the Fermat theorem. Let P be prime and let A be a subset of Z. Then A exponent P is congruent to A modulo P. Moreover, if the GCD of A and N is equal to 1, then AP minus 1 is congruent to 1 modulo N. Don't worry about this, as we are going to solve more questions on this, so you get a concept. So now let's also look at the Euler's theorem. Okay, for the Euler's theorem, let n be a positive integer and A belongs to Zn. If the GCD of A and N is equal to 1, then A exponent rho of N should be congruent to 1 modulo N. we also have roots of unity. So under roots of unity, we're going to talk about the Lagrange theorem. So we say that a Zn is an mth root of unity if a exponent m is equal to 1. Moreover, al is not equal to 1 for then we call a primitive mth root of unity. So we say that a, which belongs to Zn, is an mth root of unity if a exponent m is equal to 1. And if, moreover, a exponent L, that's the Lagrange theorem, is not equal to 1 for 0, L, and M, then we call a primitive mth root of unity. Okay, now let's look at this theorem as well. Don't worry, they are all going to make sense soon. So theorem, let P be prime if D divides P minus 1, then the equation S exponent D is equal to 1 has these solutions in Z of P. Also, let P be prime an equation Sk is equal to 1 has GCD of K P minus 1 solutions in ZP. Okay, so now that we are done with the theorems, let's look at an example to better understand these concepts. Okay, so for instance, our first example is find 43 exponent 3777 in Z100 using Euler's theorem. Okay, first of all, the first thing that you have to look at is, before we can use the Euler's theorem, the GCD of 43 and 100 should be equal to 1. So let's check. GCD of 43 and 100 is indeed equal to 1. You can use the Euclidean algorithm to check. Now, because this is equal to 1, we can continue with our Euler's theorem. So we can have this 43, then rho of 100 should now be congruent to 1 modulo 100. So looking at the Euler's theorem over here, let n be a positive integer and e, which is a subset of Zn. So in this case, our 43 is a subset of 100, okay? If the GCD of a and n, so in our case, the GCD of 43 and 100 is equal to 1, then our e exponent rho of n, so now our a is 43, exponent rho of 100 should be congruent to 1 modulo 100. Okay, now let's find rho of 100. Rho of 100 over here, is it equal to this? Can we write this as this? No, because 10 over here is not prime. Okay, so we have to resolve this equation then. So now z of 100 is equal to root of 2 squared times 5 squared. And this is equal to root of 4 times 25. Now, this 4 and 25 are co-prime from the theorem we saw previously. Because they are co-prime, we can rewrite this as root of 4 times root of 25. So root of 4 is equal to root of 2 squared, which is equal to 2 squared minus this, so 2. And root of 25 is equal to root of 5 squared, which is equal to 5 squared minus 5, equal to 25 minus 5, which is equal to 20. So root of 100 now will be equal to 2 times 20, which is equal to 40. So in other words, 43 exponent root of 100 now becomes exponent 40, and this is congruent to 1 modulo 100. Now looking at this, we have 43 exponent 40, and we have 43 exponent 377. We want this equation right here to look like the equation that was given. So now the exponent, which is 3777, is the same as, now we have an exponent of 40, so we can write this 40. How many times will 40 go into 377? So that is 94 plus a remainder of 17. So now 43 exponent 3777 can be rewritten as 43 exponent 40 94 plus 17. So now we have this 43 exponent 40 times 94 plus 17. And this is always congruent to 43 over here. This over here is always the same as the remainder, which is 17. So exponent 17, then modulo 100. So in other words, what we are trying to say is, if you have this, so this case our a is 43, so we say a then exponent 40 kill plus r, it should always be congruent to ar modulo whatever that is given, so 100. Basically that is what I'm trying to say. So in this case 43 exponent 3777 is the same as 43 17 modulo 100. So the answer you will get for this should be equal to this. Okay, now when you have 43 exponent 1, this is equal to 43. 43 exponent 2 is equal to 49. That is in modulo 100. And 43 exponent 5 is also 43. 43 exponent 9 is also 43. 43 exponent 13 is also 43. And 43 exponent 17 is also 43. So in other words, 43 exponent 17 modulo 100 is equal to 43. So the question that was given, to find 43 exponent 3777 in Z100, the answer is 43. I hope this is clear. Let's solve another example. Find 2 exponent 10,000 in Z27. Okay, so the first step is we have to find the GCD of 2 and 7. Is the GCD of 2 and 7 1? Yes. Now if it is 2 and 27. Okay, now if it is 1, then indeed we are going to get 2 row of 27 should be congruent to 1 modulo 27. Now let's find row of 27. Row of 27 is the same as row of 3 cube. And now this will be equal to 3 cube minus 3 squared. Remember the theorem? Okay, so 27 minus 9, which is equal to 18. So in other words, we're going to get 2 raised to the power 18 is congruent to 1 modulo 27. Also, 2 raised to the power 18 kil plus r is congruent to 2 raised to the power r modulo 27. Okay, so now let's resolve this. We have 18 and we're given 10,000. So now we have to find our kil and our r. So given 10,000 is equal to 18 times 555 plus 10. So now our kil, so this is the same as 18 times 555 plus 10. And this is congruent to 2. Now the remainder in this case is 10 modulo 27. So in other words, what we are trying to say is that if you are given 2 raised to the power 10,000, is the same as having 2 raised to the power 10 in mode 27. Okay, so now we know that 2 raised to the power 1 is 2, 2 raised to the power 2 is 4, this is 8, 2 raised to the power 4 is 16. We can have 2 raised to the power 8 to be equal to 2 raised to the power 8 is 2 raised to the power 4 squared. So that is 16 squared modulo 27. Then we can also have instead of 2 raised to the power 8, let's use 2 raised to the power 5. So 2 raised to the power 5 is equal to 32 and mode 27 is equal to 5. So now 2 raised to the power 10 can be resolved as 2 raised to the power 5 times 2 raised to the power 4 times 2 raised to the power 1. So 2 raised to the power 5 we add 5, 2 raised to the power 4 we add 16, and 2 raised to the power 1 is 2. So in this case we are going to get 160, and 160 modulo 27 is equal to 25. So that question that was given, which is 2 raised to the power 10,000 modulo 27, is the same as 2 raised to the power 10 modulo 27, and now this is equal to 25. I hope this is clear. Okay, now let's move on to the third example. We have 3 raised to the power 591 modulo 83. Okay, so first of all we have to find the GCD of 3 and 83, and this is indeed 1. Now if this is 1, again 3 Euler of 83 is congruent to 1 modulo 83. Now looking at 83 is a prime number. So looking at the previous examples, 27 over here was not prime, 100 was not prime, but 83 is a prime number. Now 83 is a prime number. So in this case, we're not going to use the Euler theorem, but Fermat. So we use Fermat theorem. So according to the Fermat theorem, if we have this is the same as writing rule of 83 is the same as writing 83 minus 1. So we are going to get 3 raised to the power rule of 83 minus 1 is congruent to 1 modulo 83. So 3 raised to the power 82 is congruent to 1 modulo 83. Okay, so we can rewrite this as 82Q plus R is congruent to 3, then the remainder R modulo 83. So now given this, the exponent was 591. So we have to resolve 591. So 82 will go into 591 how many times? 7 plus a remainder of 17. Meaning that we can have 3 raised to the power 82, 7 plus 17. And now this is congruent to 3 raised to the power 17 modulo 83. Okay. Now, if you have this, 3 1 is 3, 3 squared is 9, 3 cubed is 27, 3 raised to the power 4 is 81. Now 3 raised to the power 8 is 81 squared, which is equal to 4, all in modulo 83. Now 3 raised to the power 16 is equal to 4 squared, which is equal to 16. So if we want 3 raised to the power 17, it's the same as 3 raised to the power 16 times 3 raised to the power 1. And now we are going to get 16 times 3, and this is equal to 48. So this will be our final answer. So meaning that if we have 3 exponents 591 modulo 83, it is congruent to 3 raised to the power 17 modulo 83, and this is equal to 48. So this is how we use the Fermat's theorem and the Euler's theorem in an example. But one may ask, is it always the case that the GCD of A and N is going to be equal to 1? No. Let's see an example. So the fourth example is, if you have this, say 5,000 in Z22. Now the GCD of 2 and 22 is not equal to 1. So in this case, we can't use the Fermat's theorem and we can't use the Euler's theorem. So we cannot use both Euler and Fermat because GCD of A and N is not equal to 1. Okay, so now in this case, what do? We have to find the rule of 22. So rule of 22 can be resolved as rule of 2 times 11. Now, according to the theorem, remember, 2 and 11 are co-prime. And if they are co-prime, they can be rewritten as rule of 2 times rule of 11. And rule of 2 is equal to, over here, 2 is prime. So we are going to get P minus 1. So 2 minus 1, which is equal to 2. Rule of 11 is 11 is prime. So 11 minus 1, which is equal to 10. Sorry, this is not 2, but 1. So this implies that rule of 22 is equal to 1 times 10, which is equal to 10. So in other words, what we are trying to say is that if you have 2 raised to the power 5,000, this is the same as 2 raised to the power 10. 2 raised to the power 5,000 is the same as 2 raised to the power 10. And over here, we have to find 2 exponent 10. So 2 exponent 1 is 2. 2 exponent 2 is 4. 2 exponent 4 is 16. 2 exponent 8, you're going to get 16 squared. 2 exponent 5 is equal to 32. So if you want 2 exponent 10, you're going to get 2 exponent 5 times 2 exponent 4 times 2 exponent 1. And that is 32 times 16 times 2. So you're going to get 32 times 32 or modulo 22. So let me take my calculator. So 32 times 32, this is equal to 1024 modulo 22, and that is equal to 12. So 2 raised to the power 5000 modulo 22 is congruent to 2 raised to the power 10 modulo 22, and this is equal to 12. I hope this helps you. Thank you for listening. Please like, comment, subscribe, share, and also see you in the next video. Bye.